Unfortunately, North Dakota got shut down. So all y'all that are from North Dakota, we might just keep you here for a day or two because of that. Unfortunately, Mark did try to make it. He went the extra mile, and he didn't quite make it. So he is hopefully somewhere near Mandan, North Dakota right now, ready to present. He has been, for the past 23 years, contributed to research seeking to develop soil, crop, and animal management practices for the Great Plains to overcome limitations to productivity while enhancing environmental quality. And so he's going to talk to about carbon farming in the northern Great Plains, recent research findings, which will tie in with what Ben was talking about. So I'm going to let it go to the video, and then Mark will join us for a virtual Q&A.
Good morning. My name is Mark Liebig. I'm a research soil scientist with the Ag Research Service in Mandan, North Dakota. And it's my privilege to have an opportunity to share with you a little bit of the work that we've been doing at the lab here at Mandan. I'd like to start by thanking Don Flayton for the invitation to participate in your meeting, and also Vanessa Falk, who made arrangements for me to present virtually. This certainly wasn't our plans to be able to not be there with you today, but the weather and the road conditions sort of conspired against us. So it's great to be here, even though virtually. By way of a roadmap, I'm going to hopefully what I share will complement the three excellent presentations that will precede mine. I'll spend most of our time sort of talking about some of the research findings that we've had at the lab. And then with some time there at the end, I'll sort of pivot and talk about ecosystem services and a little more broadly. And so let's go ahead and get started. We've got a carbon debt in agricultural lands. We've had a substantial loss in soil organic carbon across the Great Plains, over 40%, and it's equivalent to about a fifth of carbon across the entire United States. And so it's it's substantial, and there's an opportunity to sort of address that carbon debt through adjustments in management. It's interesting at the lab how this change or this difference as a result of conversion persists over time. We have long-term treatments at the lab that some of which go back to 1916. So there's just incredible history where we can look at soil carbon stocks, and you can see how even under cropland that has been under sort of conservation practices for nearly 40 years, we still haven't been able to move our stocks back up to where they were previously. And it's particularly in the near surface depths. That's where most of the loss has occurred. And so the reasoning behind this is that the fact is that our inputs, our carbon inputs, have been less than our outputs for a long period of time. We've just taken off a fair amount of carbon in what we produce, whether that be in the products we consume or the residue that is produced. But there's also losses of erosion, mineralization, the CO2, the efflux of methane to a small degree, and maybe to a very small amount of leaching as well. So those outputs have just been greater than our inputs. To that end, it's no surprise then that we're also looking very much to new and novel practices to be able to improve soil carbon or increase soil carbon in our soils. And so whether that's through cover crops or lengthening our rotations or moving to reduced tillage systems, or maybe there's a place for perennials or amendments, or in some cases even woody crops. Everything is sort of on the table right now in terms of what we might be able to do to sort of tip those carbon inputs to being greater than carbon outputs. But it's complex. We're not just talking about carbon, which is on the right side of this graph. It's also these other greenhouse gases that we have to consider, and that we've heard about already. And you can probably get an appreciation now for how complex the management is of these other important gases that we have to take into account when looking at the overall greenhouse gas balance. But yet, it's seems like our markets ecosystem, our economic system is marching ahead with monetizing ecosystem services and specifically, carbon offsets for agricultural practices. And we've been here before. I guess I should say, about 20 years ago, the National Farmers Union here in the States put forth a carbon credit program through the Chicago Climate Exchange, and they had a pretty good run for not quite 3 years, and was able to farmers were able to benefit from those practices based on the best science that we had at the time for these offset rates. And but it went away. There was, I think, for it to really prosper, there was needed to have some changes at the federal level that never really fell into place, and so it dissipated. But you always knew it was going to come back because ecosystem markets were just sort of a thing, and it started coming back 2019, 2020. I think my first talk that I was asked to give in Wisconsin came in early 2020, and I was asked to talk about this topic. And as I was preparing my slides, one of the voices in my head sort of shouted out this quote from Mark Twain. It ain't what you don't know that gets you into trouble. It's what you know for sure that just ain't so. And I think it really sort of captured my angst, because things that had really changed over, from the CCX program to what's going on now, because the science has changed. I mean, in the early 2000s, we were relying on soil carbon stocks, mostly from near surface steps. And about 20 years later, we're still talking about carbon stocks, but we're inclusive of the entire profile. And we're also accounting for differences in bulk density, so we can get an equivalent mass on that. Our micromet methods in the early 2000s were just getting started, mostly under rangeland and also using Bowen ratio methodology. Now it's much more abundant. We could still use some more, and we're also getting these measurements on cropland, and sort of there's examples in Canada. Aaron Glenn and Brian Amiro have done fantastic work for over a decade on this, and so it's really good to see that, and that's very informative to understand sort of the temporal dynamics of carbon fluxes. And then in the early 2000s, there were just a few sites where we were measuring nitrous oxide and methane. I think back in early 2000s, it was like, Phil Robertson and Arvin Mosier. But with GraceNet coming along on the ARS side, we have a lot more people doing that. And of course, there's plenty of examples, Mario and Rich and others in Canada that are doing this work to help inform sort of the overall greenhouse gas balance. To that end, it's more than just CO2. We're also looking at these other gases because these other gases have a different capacity to trap heat in the atmosphere. So we have to account for it using this global warming potential metric. And so by doing that, we can basically get all of these three important gases sort of on the same playing field using the CO2 equivalent. And you can see the differences there in the blue box there, and how powerful some of these gases are. And so it's important to account for them together. And so I'm going to share a little bit of work that we've done at Mandan of not quite the last 20 years on this topic, sort of in two themes. I've got this soil inventory method where I'm measuring basically carbon over time, but then getting a net GWP estimate for three different types of production systems there. And then we're gonna pivot and we're gonna look at some more recent work that we've done with the micromet methods using eddy flux methodology for a couple of perennial, one perennial system, hay forage, and then also a recent paper looking at a 3-year rotation under no-till. So, okay, so let's dive into some data. This first evaluation we conducted on one of Don Tanaka's long-term studies that was started in 1993, looking at three cropping treatments: spring wheat fallow, continuous spring wheat, and spring wheat safflower rye, where the rye serves as sort of a cover crop and also a snow catch So it's sort of an early cover crop. You can see from the picture there, we used sort of the old-fashioned static chambers there for the methane and the nitrous oxide, and then looked at soil carbon change for over an 18-year period using some archive samples and then samples that we collected in 2012. Okay, so this is just one table of many from this paper, but it sort of encapsulates sort of the overall sort of net GWP assessment for each of these three systems. And I'll be using the same sort of framework for the other two studies, where you can kind of see in the left hand there the factors that account for the CO2 equivalents there. So you've got your inputs, you've got your field operations, carbon change, methane flux, nitrous oxide, and then we sum these up to get a net GWP. And so a couple of things I just want to point out. First off is that we look at just the carbon itself, and nothing too surprising here. Spring wheat fallow is losing carbon in this case. So we're a very small carbon sink under continuous spring wheat, and then where we have that 3-year rotation with the rye, that's a fairly sizable carbon sink. But when you sum up all of these factors, we're a strong source for two of the systems, and we're essentially not different from zero for that spring wheat, safflower, rye. And a lot of it has to do with these N2O emissions that we're measuring. They're particularly high under continuous spring wheat, but also even within the spring wheat, safflower, rye. And then, of course, you count for the other emissions from the inputs and the activities. It turns out that it's just not a real great story when you look at sort of within the context of sort of climate regulation services. So that's rain-fed cropping. Let's now look at what we've seen from one of our integrated system studies, study that was also established by Don Tanaka, this one in 1999. Essentially looking at cropland where it's ungrazed, but also where we have grazing, typically in the fall or early winter. Same methodology. The carbon stocks measured in this case down to about 90 centimeters over a 15-year time frame. And so what we see here is actually for the carbon change, it's pretty strong carbon sinks. But the kicker is that what we saw in N2O emissions essentially erased nearly all of the CO2 equivalent that we gained on the soil carbon side. And so you end up essentially, they cancel each other out, and you add everything up, and then both of the treatments are a net source. And I should point out that in fact the numbers are actually worse on the grazed side. We found, unfortunately, an error in our calculations for the cattle, and also for some corn yield in one of the years. And so the number for the grazed cropland is quite a bit higher. So not a positive story at all. And so yeah, it's and there's a lot of different stories in here, particularly on the N2O emissions that happen over this 3-year rotation that I could go into. Love to visit with you about, but we don't have enough time here because there's a lot of temporal dynamics that are important to consider. So one more of these evaluations, and this is actually the first one that I did going back to 2003, looking at our historical pastures that we have at the research lab. The two that differ in grazing intensity been established since 1916. The crested wheatgrass pasture was established in 1932. Same methodology for the gas fluxes. In this case, I was able to go back to our soil archive, which is just fantastic. We have 5,000 samples. Just all kinds of things you can do with that. But we found samples from 1959 that went down to 2-foot depth. And so we sampled again at the beginning of this evaluation. So it gave us a nice 44-year time step. So what do we see? Well, this is really interesting. So not too surprising, we see that all three of those treatments are really strong soil carbon sinks, and we'd expect that being in their perennial systems. But that didn't carry through to being sort of a negative net GWP for all of them, because in the crested wheatgrass pasture, so we put on a little bit of nitrogen in the fall for that particular treatment. Not an ideal sort of efficient use of nitrogen, to say the least, and that results in just a huge burst of nitrous oxide, mostly in the wintertime months. Actually, over 50% of our N2O emissions in the crested wheatgrass came from the months between November and February. So important to do annual monitoring. But so the point is that for the crested wheatgrass, we were a net source, but our two historically grazed pastures were net sinks, and they're not different here in net GWP. But if we were to take it a step further and look at this on sort of the net greenhouse gas emissions per unit of like kilogram of weight gain, you find that there you actually take up more carbon per kilogram of sort of meat, in this case, under the moderately grazed pasture compared with the heavily grazed pasture. So it's those perennial systems did a pretty good job where we did not have nitrogen applied. I should also point out, and a lot of details here, but also we had a higher grazing intensity under the crested wheatgrass pasture that does contribute, I think, to some degree, not only to the enteric fermentation, but also probably nitrogen in the form of manure and urine as well. So that can be a factor. Okay, so this is just a summary then of those three soil inventory evaluations that we conducted. You're essentially a source or neutral under dryland cropping. We found that we were a source under integrated crop livestock systems, whether they were grazed or ungrazed. And then our grazed native pastures were a greenhouse gas sink. So a bit of good news there. So now I'm gonna change over and talk a little bit of work that we've been doing more recently with our covariance methodology, looking at first the alfalfa and grass pasture over a 4-year time frame, where we were removing the forage as hay, getting a 1 to 3 cuttings off of the alfalfa and just 1 cutting off of the grass. And we did this work both on our Area 4 farm and our South Station, where we have those historical pastures. Now, this is a little bit different type of data and new for me. And we're looking at just a little bit of it. Essentially, what we have here is we got net ecosystem productivity, which is just the amount of carbon that is taken up by the system. And then we have another couple of columns that are net ecosystem carbon balance. And what that is that's the net ecosystem productivity with the carbon that is removed through hay is subtracted from that. So basically what you're taking off as your product gets subtracted from that. And so what you see here is that alfalfa does a pretty good job if you're just looking at net ecosystem productivity under quite variable conditions, I might add. 2012 was a pretty nasty drought for us, and so we were able to maintain fairly good carbon uptake. Grass, not so great. We certainly took a hit there in 2012 where things are really dry. But once you factor in the carbon that is removed through that hay, overall, we're a net carbon source. And only in 2010, where we took off just 1 cutting on the alfalfa, did our sort of a net carbon balance turn out to be sort of a positive. And so it's good to know. That's what the science tells us. We did measure soil carbon from these treatments and didn't see a difference. And I wouldn't for such a short period of time. It was only 4 years, but it was something that we felt that we needed to do. And so that's on the forages. More recently, we've taken the same methodology, this eddy covariance methodology, and applied it to a spring wheat, corn, soybean rotation. Corn and soybean is just really taken over here in sort of the central and western part of North Dakota under no-till management. So we match up there using similar size fields and doing all of our work on the Area 4 farm. And so what we see here is, same 2 columns here, net ecosystem productivity and net ecosystem carbon balance. Well, the spring wheat phase is losing carbon right from the get-go. Okay, and so that's that carbon under corn, the net ecosystem productivity under corn. Corn is a very productive crop, and so we see that as being quite positive. And then the soybean is pretty much a wash; it's pretty close to zero, with a mean of 31 grams of carbon per meter squared per year. Pretty high standard error. It's not different from zero. So that's what we're taking up or losing. But once you factor in the carbon that is taken off through that grain, everything's a loss. Okay, and I was struck by how, I've never worked with this type of data before, but I was struck, the temporal resolution was just fascinating to me. And I was struck by how short the period of time was is when we were taking up carbon over the course of the entire year. I mean, granted, we do have this long winter and so forth, but there's just it's a very compressed period of time when carbon is being taken up. And yet you have these shoulder seasons, and you can kind of pick that out in the graph where, early in the season and also later in the season where there may be some opportunities for additional carbon uptake. And so to that end, some of our we've moved on with our research there, and we've actually are incorporating cover crops in our rain-fed cropping systems, the same, spring wheat, corn, soybean rotation, seeding cover crops after wheat, interseeding cover crops into corn at about the V4 stage. And we're going to run that trial for 6 years, and we'll see what stories we have to say after that. We're also starting research looking at incorporating woody species. So that's something we'll maybe have something to say here in about 40 or 50 years. But maybe sooner we might have something to say about agrovoltaics. We're starting to get into this area of agrovoltaics. It's quite interesting to look at what carbon offset you can receive from that, considering the conventional sources of energy that we have here in the Great Plains that can actually offset a fair amount of CO2. And so the question is, how does this fit in within our agricultural systems? And we're going to be doing some research on that over the next 5 years, and maybe more, that hopefully inform those questions. And so that's a little bit on sort of the work focused on sort of the climate regulation services. But if you look at ecosystem services from our agricultural lands, there are all kinds of other things that our lands provide. And if we look at just the perennials, it's amazing what can be done not only biophysically but also the from the human dimension aspects of this, is that they have a really important part in who we are as people. And yet, our focus has been on just one aspect of all of these ecosystem services, and that's sort of regulating the composition of the chemical composition of the atmosphere, sort of getting at that mitigation aspect. And yet the social scientists who look at farmers' attitudes on climate change, they find that the whole mitigation piece just really doesn't resonate with them very well. And this is work by Arbuckle at Iowa State, surveying farmers within the Corn Belt. They're not all that keen on practices that mitigate greenhouse gases, but they're definitely thumbs up on doing things that are associated with adaptation. And so, with that in mind, it's like, well, what can we do as researchers and extension personnel and so forth to sort of find ways that adaptation practices can benefit producers, and producers are they're thinking, what can these practices provide for us in terms of greater profit or quality of life or greater yield or what have you? Does it align with my value systems? Is it something that I can test out on my farm or ranch? Okay, and I guess where I'm going with this, I'm kind of scattered right here, but what I'm going with this is that I've been, in my own experience, I've really been impressed how these soil health principles that have been around for, I don't know, about 10 years, maybe a little bit more. They've been popularized by the folks over at the Minokan farm. How well these principles resonate with producers. And what's interesting is that you can actually plug in that carbon input and output, inputs into the principles as a way to be able to talk about not only soil carbon balance, but maybe even more broadly, even overall greenhouse gas balance. And you can see what I've kind of put in there, in parentheses and how they relate. Moreover, is that if you look at these soil health principles, there's just numerous meta-analyses that are coming out. I mean, many of them are recent, but that show how they improve. A suite of things, many of them associated with improving the soil. And here's just a few examples in terms of improving your water balance through reducing evaporation. There's the improvements in soil structure, reducing erosion, and increasing your microbial biomass. If we move on to plant diversity, there's soil biological benefits from that, improved fertility, some things that are happening above ground that are important to consider, and finally this continual live root. I'm really impressed by the role of taking advantage of the shoulder seasons or incorporating perennials in and of themselves, and what that can do to improving soil physical condition, reducing erosion risk. Certainly nutrient retention is improved, and also some things on the soil biological side. Now that being said, I recognize that meta-analyses have their weaknesses, and there's always going to be an exception, because farming is very local, and so the question is that what can you take across these principles and apply in a way that sort of aligns with I guess the land attributes, and also the management expertise to maybe push a few things in the positive side to improve soil condition. And so that didn't come out very smoothly, but my point is that if we can leverage these things that resonate with producers, we can maybe improve a whole suite of different ecosystem services, and largely through improving, I think, the soil condition. And so if we can improve soil condition, soil quality, soil health, whatever you want to call it, that allows us to maybe be a bit more sort of resilient to external stressors. That will certainly increase our adaptive capacity, and that just makes us more prepared for whatever climate extremes we're going to be dealing with. And if we happen to get a climate regulation benefit associated with it, well, then great. But should that be the primary focus? I don't know. I'm not sure. So that is about it for me. I just want to thank a few people. I showed some of those tables in there that they encapsulate just so much work to get to that point. And I've been blessed by having some incredible people who've worked with me over the years. Both support scientists and technicians and postdocs, and I'm so very grateful. If it wasn't for them, it wouldn't be able to share this work with you. And I'm certainly indebted to my current team and all of my employees, my colleagues at the research lab, and also the Area 4 SCD Research Farm allows us to be doing long-term cropping systems research for nearly 40 years. So I'm very grateful. And with that, I'll go ahead and close. Thank you again for the opportunity to share a little bit of our work at the Northern Great Plains Research Lab, and hopefully there's an opportunity for us to be able to interact either by phone or by email, or if there's time, we can take questions now. So thanks again.
Thank you, Mark. We really appreciated that. I know I took a number of pictures. You have left us time for one question, maybe one really amazing question. Anybody with a question? He tried so hard. Come on, guys. We've got to have a good... Oh, yeah. That way. John Hurd. Sorry. You guys online are going, what is wrong with that girl?
Hey there. Sorry, give me half a second to organize my thoughts here. But when you were doing all your sampling, how did you account for, say, heterogeneity throughout a field that in carbon that may be related to soil redistribution due to erosion?
That's a really good question, and one that you have to account for. I didn't talk a lot about the inherent attributes of the research site that I reported on there. All of those studies were done on the same soil type. It's sort of the equivalent to like a dark brown Chernism for you in Canada. It's a Timvik, Wilton Timvik soil type, and it's mostly flat. And so for our research studies, there's just no redistribution by erosion just because things are so flat. But I fully acknowledge it's something you would have to consider if you were dealing with sloping lands.
Thank you very much, Mark, and thank you for staying safe and making the right decision yesterday. So we appreciate your time and effort.